60 degrees north of east. Here's north, west, east, south. So 60 degrees north of east would be this direction right here, where the 60 degree angle is here, because it's 60 degrees north of east. Okay? And then it says positive x-axis is pointing east, and positive y-axis is pointing north. Which coordinate of velocity is larger, x or y? So basically they want us to split this up into my x and y component vectors, and they're asking which is bigger here, x or y. Now we know our special right triangles. If you remember from geometry class, that if you call this x in a special right triangle, the hypotenuse is twice that, and the longer leg is the smaller leg times the square root of 3. So obviously this leg's bigger because it's bigger by exactly the square root of 3. So we would say that which component of velocity is larger, x or y? We would say y is bigger. Okay, the next problem, 75, says, according to the legend, a horse learned Newton's laws. When the horse was told to pull the cart, it refused, saying that if it pulled the cart forward, according to Newton's third law, there would be an equal force backwards. Thus, the forces would balance out, and the cart would not accelerate. Well, that's actually true in this situation of the free body diagram on a single point. You know, whatever force the horse pulls with, then the equal and opposite force is going to be pulling backwards, and that's true. But there's a system involved here, not just a single point. So it's true that the horse is going to feel a force pulling on it, the same force which is providing, but the horse's feet are on the ground, right? And the ground is providing some friction which allows the horse to move forward. So you have to consider the whole system and not just the single point here, because it's true that forces do act in pairs, equal and opposite, but there are other forces involved, like the friction from the horse's feet on the ground, which allow the horse to actually get grip and move forward. All right, so the next problem then says, what is the net force acting on the spring for 86? So you have 64 newtons pulling this way, and you have 128 newtons pulling this way. So what's nice about these forces, the 64 and the 128, is they're acting along the axes, which is really nice. But the 128 is not, it's at an angle. So what I'm going to do is I'm going to break that 128 into its two components, one component along the x-axis and one component along the y-axis. I'll call this x and I'll call that y just to give them names. I can find x by doing cosine of 30 equals adjacent over hypotenuse. Multiply both sides by 128, and that will give you your value for x right here, which is the x component of this force. It's actually maybe a little easier even to call whatever variable you call this one. So if I call this s, this would be s squared root of 3, and this would be 2s because that's a special right triangle we know. It's a 30, 60, 90. We learned in geometry. So one way to do this is to know that this would be 64 for s. So this would be 64 right here, and this would be 64 square root of 3 from our special right triangles. So now what we can do, if we're trying to figure out the net force, we have to add up all the x components and all the y components. So to add the x's, I have positive 64 plus a positive 64 square root of 3. Those are the two forces acting to the right. Then I have to subtract the 128 because that's acting backwards. That gives me the total for the x component, which is 46.9, and that's newtons. Now the y's, there's only one force that's acting in the y, and it's the 64, which is the y component of that 128. So that's my overall x and y. Now what I would do probably is redraw some axes and know that there's basically two components now, a component of 46.9 acting to the right, newtons, and then a component that's acting upwards of 64. And so the overall resultant is this red vector that goes tail to tip. And I can find that pretty easily by doing the Pythagorean theorem. So it's a squared plus b squared equals, I'll call this c for now, equals c squared. And so we can solve for that hypotenuse of that triangle, which is the overall resultant force of adding the other three together, which we get 79.3 newtons. So the overall force is 73.9 newtons. We can also figure out the angle because the problem asks for the net force. Net force is a vector, so that gives us both a magnitude, which is 73.9, and an angle. To find the angle, we're going to do tangent of theta equals opposite over adjacent, and we can do inverse tangent then of 64 over 46.9, which gives us about 53.8 degrees. So we would say our final answer is 73.9 newtons at 53.8 degrees and that would be north of east. There's our vector for net force. All right, the next one says a ship's due in port, so it starts off at its original position, and it's due in port 500 kilometers due south, so you would be the port. But a wind comes and blows it 100 kilometers east. So the question is, this is the right triangle, we got to find the hypotenuse. If you do that with Pythagorean theorem, you get 509.9 kilometers. And then it also says, in what direction must it travel? So we can find this angle right here, theta. We can find that by doing opposite over adjacent, so we can do tangent of theta equals opposite over adjacent. We can do inverse tangent of 500 over 100, and that gives us that angle, which is 78.7. 78.7 degrees. And then we'd have to say that correctly, so that would be like south of west. So that'd be south of west. And you can actually have found this angle right here instead. Take 90 minus the 78.7 and find this angle, and then you just have to describe it as west of south instead of south of west. So there are two different ways to do it. Okay, the next problem then says that you're driving a 2,500 kilogram car at a constant speed of 14 meters per second along a wet but straight level road. As you approach the intersection, the traffic light turns red, you slam on the brakes, the car's wheels lock, and the tires begin skidding. The car slides to a halt in a distance of 25 meters. What is the coefficient of kinetic friction between your tires and the wet road? Okay, the key is going to be a free body diagram for these. We need to look at the forces that are acting on the car. When we slam on the brakes, there's only one force acting on the car, and that's the force of friction. That force of friction is equal to the coefficient of kinetic friction times the normal force. So we need to find, it's also equal to ma. Every force is equal to ma. So because we were given a distance and velocity, we can find actually this quantity, which is the mass times the acceleration, and we can set it equal to this. So this is the equation we're going to use right here. All right, the normal force is mg. So I'm going to write mg right there. So it's mu sub k times mg. The mass is 2,500. Gravity is 9.8. And that's equal to the mass, which is 2,500. So we actually don't even need the mass, because that just cancels from both sides of the equation. We need the acceleration that the car is actually decelerating by, though. And in order to find that, we need to figure out what formula to use. So let's use final velocity squared equals initial velocity squared plus 2 bar change in distance. Final velocity is 0. The initial velocity is 14. And the acceleration's what we're trying to find. The change in distance is 25 meters. So if you solve this, and we can ignore negatives because technically that acceleration is going to be negative, meaning that it's pointing to the left. If we call positive to the right. But if you solve this for A, you get 3.92, and that's meters per second squared. That's our average acceleration that we're slowing down with. That goes right here. And so all we need to do to find the coefficient of kinetic friction is divide by 9.8. So that's 3.92 divided by 9.8, which gives us 0.4. All right, 95 says an object in equilibrium has three forces exerted on it. A 33 Newton force acts at a 90-degree angle from the x-axis, so I'm going to imagine some x and y-axis here. Okay, and then we have 33 Newton force acting at a 90-degree, so I'll call that this force right here. And then a 44 Newton force acts at a 60-degree from the x-axis, so that would be a bigger force acting at a 60-degree angle. And then what are the magnitude and direction of the third force? So the third force is obviously going to have to be back somewhat this way. And we need to find out what that is. So what we're going to do is we're going to add these two together. I'm going to make this one in component form. So I'm going to switch this into an x and y coordinate. Now, I'm going to use special red triangles just because I think it's a little quicker. But if I call this 2x, this would be x, and this would be x squared of 3. So basically, I can just take 33 divided by 2 to find this one. And this one's 33 divided by 2 times the square root of 3. If you remember your special right triangles. So I'm going to add those together. The x components, if I add them together, I'm sorry, this 33 goes to the other force over here, so I didn't label this very well. This is 33, and this is 44. So this would be 44 over 2, and this would be 44 over 2. So the forces in the x direction are just the 44 over 2 times the square root of 3 newtons. And the force in the y direction, there's two of them. There's the 33 plus the, I'm sorry, this is 44 over 2 square root of 3 in the y, and then in the x there's just the 44 over 2, which is 22. So 22 and 22 square root of 3. This is 22 square root of 3. So in the y's we get 22 square root of 3 plus 33, and then in the x we just get the 22. Alright, now I'm going to redraw those on another coordinate here. So I'm going to go over 22 and up 33 plus 22 square root of 3 and make a new triangle, because that's the resultant. The resultant goes off like that. And I'm going to find it real quick. So this is 22, and this is 33 plus 22 square root of 3. I'm going to do the Pythagorean theorem with these numbers real quick to find the overall magnitude, which gives me about 74.4 newtons. Now that's got to be exactly the same magnitude of the resultant. That's got to be going the other way, because they have to cancel out and be in equilibrium. So I know this one has to be 74.4 newtons. And then if I figure out this angle, like the angle, either one of these angles, I can then describe this angle using simple geometry. So figure out the angle with tangent, do tangent of, I'll call this theta, equals opposite, which is this number, 33 plus 22 square root of 3 over 22. And that gives me, do the inverse tangent of that, and you get theta equals, that'd be 72.8 degrees. Now, that's this angle right here, so it's a little hard to see from my picture, but that's this angle all the way up to here. And if that's that angle, then basically that's this angle down here as well, because those are vertical angles. So this is 72.8 degrees. I can describe that as 72.8 degrees south of west or something, or just say 72.8 degrees with the x-axis, and that's good enough. So 74.4 newtons and 72.8 degrees with the x-axis. The answer key might have 252.8, and that's because, if you add 180, you're going around all the way to this angle over here. So you're adding 180 to 72.8 to give this angle. So that'd be a great answer as well. Okay, the next problem gives us a sign that's hanging by two cables. And the weight of that sign they give us is 7.5 times 10 to the 2 newtons. And it makes a 30-degree angle. This cable makes a 30-degree angle right here. They want to know the tension in cable B right there. So this is a tough problem. We're going to have to basically break it down into x and y, and we're going to have to write a system of equations based on the tension in the cable. So I'll call this the tension in cable A and the tension in cable B. And in the x direction, I have the tension in cable B has to be exactly equal to the x component of the tension in cable A, which that would be this force right here. Those have to cancel each other out, the B and the A, because it's in equilibrium. So what I'm going to do is call that x for now. Now I'll do the sine of 30 equals opposite over hypotenuse. And I'll multiply both sides by the tension in A, and I'll use that right here. So this has to be the tension in A times the sine of 30. So in the y direction, I have the tension in cable A pulling up. I'll call that y for now, and I'll find it real quick. So that would be cosine of 30 degrees equals adjacent over hypotenuse. Multiply both sides by t of A. So this force right here is pulling up would be t sub A cosine of 30. And it's got to be equal to the force that's pulling down, which is mg, and which is 7.5 times 10 to the 2 newtons. So I'm going to solve for t sub A then from this equation right here. I guess I didn't need a system after all. I will have the tension in cable A equals this number right here, which is 866.03 newtons. And they actually wanted the tension in cable B though, so I'm going to have to multiply that by the sine of 30 to get the tension in cable B. Tension in cable B is 433